Welcome back. In this video, we will learn about ANOVA, that is Analysis of Variance. What is it actually? So, it is a tester of null hypothesis. That means you can test a null hypothesis whether that null hypothesis should be rejected or not to be rejected. Now, what it does, that is what it tests actually. It tests the equality of two or more population means. That means you have some populations, so you can say whether the means of those populations are equal or not. How it does? You have the sample from those populations because you do not have the population data. So you take the samples of those populations and you calculate the variances of those samples. You analyze them and you can comment or you can test whether the population means are equal or not. For example, you have three populations like this. So population 1, 2 and 3. They have their own means, mu1, mu2 and mu3, but you do not know actually what is the mu1, mu2 and mu3. So you take the samples from these populations. So this one is sample 1 from population 1, this one is sample 2 from population 2, and this one is sample 3 from population 3. You calculate the variances of these populations, of these samples, and based on the calculation of those variances, you can comment whether the means of the populations are equal or not. So based on the variances of those samples, you can comment on the population means. So this is a very powerful tool for testing this kind of hypothesis, right? So there are three types of ANOVA. One-way ANOVA, which is dealing with one factor or independent variable. There is a two-way ANOVA, where two factors or two independent variables are involved. And there is another one that is MANOVA, which is multivariate ANOVA, that involves multiple factors or independent variables. Now, in this video, we will deal with one-way ANOVA. This is a snapshot of a movie dataset, and you can see there are variables like this: movie title, genre, viewer score, actor score, budget, and ROI. ROI means return on investment. That means how much revenue the production company is earning after exhibition of the movies, right? Now, out of these variables, we have selected genre because we are dealing with one-way ANOVA. So, you have to select only one factor, and that is genre. So, in this genre variable, you have three types of data. That is romantic, sci-fi, and comedy, right? So, here we go. This is a sample 1 we have taken from sci-fi movies, and we talked to 4 viewers and they gave the score of 89, 78, 91 and 84. So these are the 4 scores given by 4 viewers who have seen sci-fi movies. We go for the sample mean, that is x1 bar. The suffix 1 actually indicates sample 1. So x1 bar gives you 85.50 as a mean score, right? Next, we go to another cinema hall and their comedy movie is going on. So we talked to 4 viewers over there also, and they gave the score 67, 77, 81 and 76. And we go for the sample mean, that is x2 bar. The 2 indicates sample 2 and the mean score comes out as 75.25. Similarly, from sample 3, for the romantic movies, we talked to 4 viewers again, and the sample score is, the sample mean is 80.25. Now, we have taken for simplicity as the sample size as 4 in each cases. So, you can have different sample sizes, no problem. Now, what you see here, the sample means are not equal. Now, the question is, can you say from these 3 sample means that the population means are equal? That means the mean score of all the sci-fi movies is equal to the mean score of all the comedy movies, which is equal to the mean score of all the romantic movies. So that is tested by ANOVA. So here is a roadmap. You take the samples, you calculate the variances. Next, you go for the F score. It's a very simple, very simple, small formula. And after getting the score, you consult the F table, that is F distribution table, to test the equality of the population means, right? So these are the steps. In step 1, you set up the null hypothesis first. What you want to know or what you want to test. So that is a question. So the null hypothesis will say that all the means are equal, because null hypothesis always tries to be in neutral position. It does not care about the effects. That means whether it is a sci-fi movie or a comedy movie or a romantic movie, these genre types do not have any kind of effect on the scores. Null hypothesis wants to say that. So our null hypothesis will be all the means will be same, right? Next one, calculate the variances of the given samples. Next, calculate the degrees of freedom and calculate the F-score of the given samples. And finally, you consult the F-table and take decision whether your null hypothesis should be rejected or not to be rejected, right? Before going into the procedure, I will introduce you with two terms. The first one is variation. Variation is not equal to variance, right? So see, what is variation? It is a sum of squared deviations from an arbitrary point A. That means it is just a sum, right? So you give the summation sign over here. I equal to 1 to n xi minus a whole squared. That means if your n is 3, suppose your n is 3, then you find the gap x1 minus any arbitrary point A and you square it, plus x2 minus a, you find the gap and you square it, and here x3 minus a and you square it. So you add these squared terms and you get variation. Clear? So if your arbitrary point A is the mean of that data points, right? So that is also a variation. So in place of A, we have written here x bar, right? So this is only the difference between the first line and the second line. Now, what is variance then? Variance is the mean of those squared deviations from x mean. That means whatever you have got over here, not here, over here, from the mean actually, you take the mean of those squared deviations. So it will go like this, x1 minus x bar, that is from the mean, you take the gap and square it, plus x2 minus x bar, you take the gap and square it, then plus x3 minus x bar, you square it, you add these terms, okay, and divide it by n, that means slash n, that means the number of terms, that means 3 here, divide it by 3. That means you are taking the mean of these squared deviations, right? So this is the first squared deviation, this is the second squared deviation, and this is the third squared deviation. You take the mean of those squared deviations, and that mean we call variance. So variation is the sum, or here in this case, variation is the sum of the squared deviations from mean, and whenever you take the mean of that variation, we call it variance. So variance is actually the variation from mean divided by the number of observations n. Clear? Okay. So here we go with the data points, the previous data points, we are reusing it here. So first, set up the null hypothesis. So what will be our null hypothesis? The population mean scores are statistically equal across all the 3 types of movies, right? So you write here 3 types of movies, right? So you say that mu1 is equal to mu2 is equal to mu3. So this is our null hypothesis. Clear? And alternative hypothesis will be at least one population mean score is not statistical equal. That means it may happen like this, that mu1 is equal to mu2, but it is not equal to mu3. So if it goes like this, or it may happen that these two are equal, but this is not equal. So any one of these means is different from the other two means, then your null hypothesis fails and you should reject the null hypothesis. Correct? The next is step 2, calculate the F score. What is F score? It is nothing. The statistic actually, this is F score. So it is actually the variance between by variance within. So this is just a ratio. Clear? So what is variance between and what is variance within? So variance between is actually the variance between samples. So the variance between this sample, and this sample. Right? So this is actually we call variance between. Between is between the samples. Right? And in the denominator, you find that variance within. That means mean of the sample variances. That means you have some sample variance over here, that is V1. Here you have sample variance V2. You have sample variance V3. Okay. So you take the mean of these three. That means you add these variances and divide it by 3. So that will be your variance within. So for that, you need the mean of each sample, right? So to find out the V1, you need the mean of the sci-fi movies. For V2, you need the mean of the comedy movies, right? So here we go with the means. This x1 bar is 85.5. The next one is x2 bar, that is 75.25, and the x3 bar is 80.25. So you have got the means of these three samples separately, right? So visualization will be like this. You have the sci-fi movies, the samples over here, the 4 data points. These are the comedy movie data points, and these are the romantic movie data points. Now here we have the mean of the sci-fi movies, that is x1 bar is 85.5. Similarly, we have the mean of the comedy movies and the mean of the romantic movies, right? Now, if find out the gaps between the mean and those 4 data points over here, then you square it, you square this gap, you square this gap also, you square this gap also, and you square this gap also. So find out the gaps and square those gaps, okay? So those gaps are actually we call deviations, right? So similarly, you do with these things also. You find out the gap and square it. You find out the gap and square it. Then this one, square it, and this gap and square it, right? So the calculation goes like this. You remember this thing that this is one is variation, not variance. First, you have to go for the variation, that is the sum of the squared deviations. Then we will go for variance, right? So you see here, J is running from 1 to C. Here C is 3. C is equal to 3 and R is equal to 4. See, J is running this side. That means this is running from 1, then 2, then C equal to 3 here. And here this side is row. So it is 1, 2, 3 and R equal to 4, right? So this side I is running. So the first one is that xij minus xj bar. Now see this first one j is 1 and I is also 1 first time, right? So in that case xij means x11 minus x1 bar. So x11 means 89 and x1 bar means 85.5, right? So you have written here 89 and 85.5. You find out the gap, there's a deviation, and you square it, right? Next, j remains as 1, I becomes 2 now. So when I becomes 2, so this one becomes 2, that is x21, and x1 remains same because j is 1. So j is 1, I is 2. That means x21 minus x1 bar. So x21 means 78. So 78 minus x1 bar, the same mean, 85.5. So here you go, 78 minus 85.5. You take out the gap, there's a deviation, then you square it, and then go for the third addition. In this way, you go on for 12 deviations, because there are 12 data points, so you have 12 deviations, squared deviations, and you finally got this 598.5. So this is the variation within. Clear? Okay, we go for visualization again. Now we have to go for variance between the numerator. So for that numerator, we need grand mean. So here we go with the grand mean. How will you find the grand mean? Grand mean's notation is x bar bar, the double bar. It's very simple. You add these three means of these three samples, that is x1 bar plus x2 bar plus x3 bar, and you divide it by 3. And you get this 80.33. So here is your grand mean here, right? So you can also go for adding these 12 data points and divide that sum by 12. It will also give you the same value, 80.33, right? Now what you do? You find out the gaps between the means of those samples and the grand mean. So x1 bar minus x double bar, you find out the deviation, then you square it. For the second sample, you start from the mean and take the deviation up to x bar bar. So this one also squared, and this one also squared. So this time you are taking the deviation from the grand mean up to the individual means of those samples, right? Now you add these squared gaps and you will find the variation between. So here we go with the variation between. Here you see these are the gaps. 85.5 is your mean of the first sample, and this is the grand mean. So you find out the gap between these two and then square it. The same thing goes with the other means also. This is the second sample's mean minus the grand mean. You square it. This is the third sample's mean, and this is the grand mean. You take the gap and square it. Now the point is that what is this R1 doing here, what this R2 is doing here, and what is this R3 is doing here. These deviations, these squared deviations between the sample means and the grand mean must be an weighted deviation. That is a weighted squared deviation. So how will you give the weight? So these weights are actually given by the row count. That means how many samples, how many sampling points are there in each sample, because these are sampling points. These are not samples, these are sampling points. So there are 4 sampling points in the first sample, 4 sampling points in the second sample, and 4 sampling points in the third sample. So in this case, we have taken the sampling points as 4 in all the 3 samples. So R1 is 4, so this 4 is here. R2 is 4, so this 4 is here. And R3 is 4, so this 4 is here. Now when you calculate this thing, you will get 210.17. So this is your variation between. So this is your variation within, and this is your variation between. But we need variance. We need variance between and variance within. So you have to go for variances now. So you have got this variation between as this. I have repeated that thing for your reference, and this is variation within this one, right? Now what is variance between? Because this is a sample we are dealing with. We are not dealing with population but sample. So we have to divide the variation between with the degree of freedom between. That means whatever the degree of freedom is coming out, we are not dividing it by sample size or something like that. We are dividing it by the degree of freedom. Why we use degree of freedom instead of the sample size 4? Because you keep in mind that these are samples. These are not populations. Now, when you go for random sampling, then you have some sampling error, which we call sampling error. Now, these sampling errors are like that every time you go for some random sampling, you have different data over here, and whenever the data changes, your sample means are also changing. So, in a second sample set, you may have that x1 bar is the lowest and the x2 bar is the highest. So whatever the sample we have taken over here, that may be biased. So to minimize that bias, we go for degree of freedom in case of samples. So variation between is divided by the degree of freedom. So degree of freedom is always -1. We have 3 samples over here. So the value of C is 3. So we are dealing with between. Whenever you are dealing with between, we are dealing across the samples. And whenever we are dealing with within, we are dealing within the samples, right? So the number of samples is 3. So 3 minus 1 gives you 2. So the degree of freedom between is 2. So divide this 210.17, that is a variation, divided by 2, and you would get 105.09 as your variance between. Similarly, we will go for variance within. Now, in case of variance within, we have to divide the variation within by the DOF within. Now, what is the DOF within now in this case? We have 3 samples. For each sample, you have the sample size -1. So the first sample size is R1 and -1. This will give you the DOF for the sample 1. The R2, that is the sample size for the second sample, that is also done with -1. So this one will give you the degree of freedom for the sample 2. And this one will give you the degree of freedom for sample 3. Now you add these 3 and you will get n minus 3, because n is your total sample size, and this R1 plus R2 plus R3, this will give you 9 actually, this will give you 12. So this will give you 12, and -1 minus 1 minus 1 will give you -3, and ultimately this will give you 9. So you divide the variation, what you have calculated before, that is 598.5 divided by 9, this will give you 66.5. So you have got the numerator as well as the denominator. So it's very simple. You just take out the ratio and you will get 1.58, right? Now we will go for consulting the F table. Now before that, we have to take a decision on the significance level alpha, whether it will be 0.1 or 0.5 like that. So in this example, we have taken 0.1, okay, as our significance level alpha. So here is our table I have taken from the website, one website, and here on this side, one DF1, this is DF1, this side is DF1, and this side is DF2. This DF1 is actually for the numerator, so DF1 on the upper side and the DF2 on the lower side, right? So DF1 is meant for DOF between, so DOF between on the upper side, and the row side, it is DOF within, right? So DOF within, right? So what is our DOF between? So DOF between is 2 here, you can see. So this is the required column we have to consult, and in case of DOF within, the value is 9. So we have to go for this row, okay? So this column and this row is here. This is the cell we can come up with, and this cell talks about 3.00645 as the critical value, right? So from here we have taken here 3.0065. So this is our critical value. Now your null hypothesis will be retained, or you will not reject the null hypothesis if your test score is below 3.0065. Now our score is 1.58, right, which is pretty low than our 3.0065. It is lower than 3.00645. So it is within the range. So we do not reject the null hypothesis. So the F value is lesser than critical value. So the null hypothesis is not rejected in this case. That means whatever the sample means show us that they are different, but our test score shows that actually the population means are same. That means the sci-fi, comedy or romantic type movies do not have any kind of effect on the viewer score. So this is our conclusion. I hope you learned about the ANOVA and what is the purpose of ANOVA. Remember that take the sample variances, and by analyzing the sample variances, you talk about population means. Okay. Now, one thing I should mention you here that in case of t-test, you will find the same thing, but in that case, only 2 population means and only 2 samples you can deal with, right? So it is limited up to 2. So you can say that ANOVA is a more generalized version of t-test. In the next video, we will go for Bonferroni approach. This is used to identify which samples represent 2 different populations. So this is the thing we need. ANOVA says whether your mu1 is equal to mu2 or equal to mu3 and whether it is not. In case it says that null hypothesis should be rejected, that means at least one of these means is different from the other means, right? Now, which mean is different? So that is a question. So that answer is not given by ANOVA. So for that, we have to go for Bonferroni approach. It will say which mean is actually different. So I will meet you all in the next video.